Okay, let's take a look at the VI graph for an ohmic resistance and for a non-ohmic one. So in this case, for ohmic resistance, the VI graph will be a straight line. For two different potential that's applied across the ohmic resistor, you will find that VA divided by IA is equal to VB divided by IB. So we can conclude that RA and RB is the same. In this case, the gradient of the straight line is actually the resistance, and that is actually a constant value. To explain that at a microscopic level, what happened in an ohmic resistor is that as the potential difference across the resistance increases, the drift velocity of the electrons increases, and because of that, the current also increases as well. And that allows R to be kept as a constant. In the case of a non-ohmic resistor, in this example that we're studying, it's actually a filament bulb. So in this case, you will see that if the potential difference applied is VA versus a higher value of VB, the resistance differ. How we calculate the resistance is the same as what we did on the other side, which is VA divided by IA and VB divided by IB. So in this case, the resistance RB become higher than RA. As the potential difference applied across the non-ohmic resistor increases, there will be greater heat dissipation within the non-ohmic resistor, and as a consequence, temperature will increase. When temperature increases, the vibrational motion of the lattice ion increases, and the charge carriers per unit volume will also increase as well. With a higher charge carriers per unit volume, one would have expected the current flow to increase. However, the higher vibrational motion of the lattice energy impedes the electron flow and reduces the drift velocity of the electrons. So hence, the resistance increases. Do take note that there are two types of graph. You can have the VI graph, those that we used earlier, or at times, they can instead give you the IB graph. So if they give you the IB graph, and this is the same graph for the filament bulb, you will find that you still ought to be able to conclude that resistance at B is higher than A. We have covered the ohmic resistance and also the filament bulb. And now we'll look at the thermistor. In the A-level syllabus, we're looking at NTC, which is negative temperature coefficient thermistors, where the resistance, in fact, decreases as the temperature increases. So that is depicted in the IB graph, and the resistance at this point, B, will be lower than the resistance at A. And at a microscopic level, what is happening is that at a higher temperature, you get greater kinetic energy of the atoms, like we explained earlier. So the vibrational motion of the lattice ion increases, and that impedes the current flow. However, we also know that the drift velocity will also increase with higher potential difference, and we also expect a significant increase in the number of electron density. The increase in the electron density outweighs all other factors. That's the reason why the current increases more and the resistance drops. A quick way to help you remember that filament bulb's resistance increases is using the short form Fi. So F is filament, I stand for increase. As the potential difference increases, the resistance increases. Thermistors can we remember with the short form TR. So thermistor resistance reduces. So we can remember that as the potential difference increases, the resistance of the thermistor decreases. Finally, we take a look at the diode. A quick introduction of diode is that there is a need for a certain voltage before it becomes a conductor. The stretch that you see down here, where current is 0, indicates that it is an insulator. It doesn't allow any current flow. So when the potential difference applied is actually higher than this value V0, the diode will start behaving as a conductor, and the resistance actually decreases as the potential difference increases. Very similar to that of the thermistor. When the potential difference is larger than V0, the resistance of the diode decreases as the potential difference increases, similar to that of a thermistor. Or this behavior is what we term as forward bias. Reverse bias occurs when the potential difference is applied across it is negative, and this potential difference here is called the VB. So beyond VB, the diode would have broken down and it will behave no different from a normal conducting wire. Let us take a look at this example. So in these questions, we actually have a 3-volt battery connected to a thermistor and as well as a 10 ohm resistor. And the IV graphs is given as such. Since both of them are connected in series, we expect the potential difference across the thermistor plus the potential difference across the 10 ohm resistor to be equal to 3 volt. And we also know that the current flowing through them should be the same. Let's hypothetically assume that the current flow is 0.2 ampere. So if the current flow is 0.2 ampere, we will know that the potential difference across the resistor will be 2 volts, and the potential difference across the thermistor will be 3 volt. So in this case, it's not possible because both these numbers should add up to 5 volt, and obviously it's not. So let us decrease the current flow to 0.1 ampere. So at 0.1 ampere, the potential difference across the resistor is now 1 volt, and the potential difference across the thermistor is 2 volt. So in this case, we can conclude that the current flow is 0.1 ampere. So that's the answer. Using the same VI graph, what happens if we decide to connect the thermistor and the 10 ohm resistor in parallel? Using the same battery with an EMF of 3 volt. So in this case, we know the potential difference across both the thermistor and as well as the 10 ohm is 3 volt. So we can look for 3 volts and extrapolate from here. So in this case, the current flow through the thermistor is actually 0.20 ampere, while the current flow through the resistor is 0.30 ampere. And if we were to put an emitter around here, then the total current that's flowing out from the battery will be 0.50 ampere. So that's actually how we use a VI graph to solve electric circuit problems.